including all possible determinants, that's called full CI, as I said before, and everything else then is called truncated CI. And as I mentioned before, I mean, I sort of talk about these kind of different contributions and issues in the context now of CI because it's conceptually the simplest one, but it applies to all the other methods, metal-pressure perturbation theory and coupled cluster theory as well. So, if you only want to have truncated CIs, they include only certain classes of the determinants, and classes or types or whatever you want to call them, single excited, double excited, triple, quadruple excited determinants. And the simplest one, of course, would be only single excited determinants, which you then could call, or is called, CIS for CI singles. Not some kind of whatever CIS is also called. But if I would do a CI calculation with that approach, including single excited determinants, what is the energy what I get out of that? Emil? That's just Hartree-Fock energy. So that's not a method for including correlation in your ground state. But that is actually the simplest method for treating excited states. So it's the simplest method for excited states. Because what you do then is your excited state wave function, you write it as a linear combination of all singly excited determinants. So you have a summation over here, and then you need some coefficient. And where do you put them? Just there, like this. You need some coefficients. And what you do then in your CI single calculation, you set up that matrix, and you get those coefficients. You diagonalizes. You get as the eigenvectors those coefficients, and you get energies which then are approximated to your excited state energies. And those coefficients then actually you can also look at, and we're going to do that maybe in a few weeks, because those coefficients are the ones, I mean, how you combine those determinants. Each of that determinant that we can write up, that's a simple picture, because if you have some occupied orbitals, some virtual orbitals, then there was here an occupied orbital I, and there a virtual orbital A. If those have been occupied, it looks like this, and this determinant then just corresponds to that you moved one electron from the occupied orbital I to up to here. So this is sort of a simple one electron excitation picture. And then those coefficients tell you how large or how much this simple from one occupied orbital to one virtual orbital, sort of in like HOMO-LUMO transition kind. Here was HOMO -1 to LUMO +1 transition. How much that contributes to your excited state. And sometimes, obviously not always, but sometimes it might be that you have, or maybe not like this, but you really sort of have the HOMO-LUMO. This is the HOMO, the highest occupied molecular orbital, and the lowest unoccupied molecular orbital. The coefficient for this transition, for this determinant, is 90%. And then your sort of one electron picture that this is a HOMO-LUMO transition actually holds. In general, this is not going to be the case. If you're lucky, then it's maybe 50%. So, and then you have, for the rest 40%, you have basically all the other ones contributing. But still you can sort of look at them and see, is there a main contribution? what orbitals are that is that the sigma to sigma star or pi to pi star transition I actually was looking for. So CI singles is that. That's the simplest approach for excited states. There's also another word for it. In this context, it's also called the Tam-Dankov approximation. But we might come back to that when we talk about properties in a few weeks. Now, but if you're interested in the ground state, singles is not the way to go. So we should go to doubly excited, so something which is called CID, CI doubles. And there are a few comments we can make about doubles excited determinants. The doubles excited determinants these are the most important contributions. And again, never mind whether it's configuration interaction, Müller-Blesa perturbation theory, or coupled cluster theory, the double excited determinants are the most important contributions. And there are several reasons for that. Reason number one is the double excited determinants, that's right, Hartree-Fock, Hamiltonian, and then some I, J, A, B, a double excited determinant. Those are the only ones which directly couple with the Hartree-Fock determinant. Triple excited cannot, because that's the difference in 3 orbitals. Single excited are not because of the Brownian theorem. So the only ones which really directly couple to the Hartree-Fock are the double excited determinants. Secondly, we're going to see next week when we do perturbation theory, Müller-Blesa perturbation theory, that in the first order of Müller-Blesa perturbation theory, again, it's only the doubles which contribute. But you actually can look at it in another way also. Now, electron-electron correlation is, compared to the Hartree-Fock model, is some kind of a perturbation. Our orbitals are derived based on this average, the mean field interaction with the other electrons. Now, having the full Hamiltonian, we have the full interaction there, and that's sort of that's an interaction which is not included in the derivation of the orbitals. So it's something which is going to perturb the orbitals. So we can look at, in general, if I have some orbitals, and that's the occupied orbitals, and I have some perturbation present. So the orbitals are going to be changed. I mean, they change. They should be different. They should adjust to the new situation. And how can we do that? I mean, we can take the original orbital, sort of start off with that, and make some correction. And one way, and sort of add some correction, the simplest way to is, I mean, we have to add some other function to it to correct it. And of course we want to stay in the picture we are. We don't want to introduce something new. So what could we add? We could add some of the other orbitals. So we could sort of add some orbitals, also the unperturbed, with some coefficients. Now the question is, which orbitals should that be? We could add some of the other occupied orbitals. That would change that orbital I, if I add some of the other ones. It sounds like a good idea, but there's something about determinants which you should remember. What happens if you add a multiple of one column to one of the other columns of the determinant? What happens for the value of the determinant? Nikolai?
doesn't change?
It doesn't change, nothing happens. Which means if I make a linear combination of the occupied orbitals in the Hartree-Fock determinant, the orbitals change, so I could go maybe from these canonical delocalized orbitals which we get to some localized orbitals. But the Hartree-Fock wave function is still the same. Because the determinant, and the determinant doesn't change if you add multiples of one column to another one, or rows. You also could do it with rows, but so that makes no, I mean, you can do that, but it doesn't bring some new information in. So it's not the occupied orbitals, it has to be the virtual orbitals. So we can change our occupied orbitals by mixing in some of the virtual orbitals. And that mixing in is sort of will allow to adjust to that perturbation. And then, of course, we can correct our wave function. So if we want to have a perturbed wave function, we could start off with our Hartree-Fock and then add determinants to them where we used our perturbed orbitals. Or basically, said in another way, we make a determinant, a Hartree-Fock determinant, but now with those perturbed orbitals. So if we insert the perturbed orbitals in our Hartree-Fock determinant, and then we can sort of split that up, so we get the original unperturbed Hartree-Fock determinant, and then we get a sum over, actually a sum over all singly excited determinants with the coefficient then, I guess. Say and that's actually, we're going to see that later when we talk about properties, if you want to describe the effect of an electric field. The orbitals are going to change due to electric field, in case of dipole moment or polarizability. And that is essentially means that we mix in single excited determinants into the Hartree-Fock determinant in order to describe that. That's another place where the single excited determinants are actually important if you want to describe perturbation. But now we're not looking at electric field, we're looking at two electrons interacting with each other. And that means it's not just one electron and its orbital is perturbed by something outside of the system, but it's two electrons which are perturbing each other, which means it's actually two orbitals which are at the same time perturbed. So for electron correlation problem, we have not only one orbital, but we actually have two orbitals. Two orbitals perturbed. And then if I want to do the same trick again, then I end up with a Hartree-Fock plus a linear combination of all double excited determinants. With some coefficients. So, including those double excited determinants in our wave function is really describing that I have a correlation between a pair of orbitals. They both get perturbed, and therefore I mix in both orbitals, I mix in some virtual orbitals in order to account for that perturbation, allow for the perturbation. And if I do that with two, I get a double excited determinant instead of. So having those double excited determinants means I include the correlation between pairs of orbitals. They are pairwise, they are allowed to change, to be perturbed. And again, I mean, it's the most important is a pair of orbitals, two electrons interacting with each other. So therefore the double excited determinants are also sort of on physical grounds, and not only technical grounds, the most important contributions. And that's sort of, I mean, you could call that pair correlation. So doubles are the most important ones. The singles, they don't directly give a contribution, but they are not so many, actually only a few. So the actually cheapest method which is really used is that configuration, interaction, single and doubles. That's the simplest DI method. CI method. It scales with the number of basis function to the 6th power. Remember, the integral transformation was n to the 5th. That is 1 power higher than is n to the 6th. How much of the electron correlation or the correlation energy you get sort of like, what is that, 80 to 90%. 80 to 90% of the correlation energy. You would get.